Okay, so remember with slope fields, we actually need to consider what we're substituting into. All of our x values are going to be substituted in for x, and all of the y values are going to be substituted in for the y. So here, if I have -3 divided by -3, we get 1. And similarly, if I want to consider what would be nice and easy to graph, -2 divided by -2 would be 1. So would -1 over -1. However, 0 divided by 0, not as a limit, but just as a value. Dividing by 0 always wins, so it's fine. And then 1 over 1 is 1, 2 over 2 is 1, 3 over 3 is 1. Okay, so now if I look at where I would have 0, whenever x is 0, except when we're dividing by 0, we'll have a 0 slope. And wherever y is 0, we'll have an undefined slope. And undefined is going to be 0 every time when we're talking about substituting values into a function. Okay, so next I would consider where y is equal to 1. If y is equal to 1, then we're dividing by 1. That makes it easy to do, because -3, -2, -1, 1, 2, and 3 are relatively easy. Similarly, when we have y equal to -1, then the x value is just really multiplied by -1. So we'd have 3, 2, 1, 0, -1, -2, -3. So then if we evaluate the other values, we can start with x being -3 and y being 3 and get -1. And so if we start to notice a pattern here, we have +1 along this diagonal. I'll have -1 along the next diagonal. Okay, so in the next value, if I have -2 for x and 3 for y, we have -2/3. We would have -1/3. For the next value, we're going to have 1/3, 2/3, and then again 1. So notice how we have a mirror image, that negatives are positives. Okay, so if we go across here, we would have x is -3, y is +2, so we'd have -3/2. We have -1 and -1/2. Similarly, we have 1/2, 1, and 3/2. Okay, so if we check this value, we have -1 for x and -2 for y, we have +1/2. -1 for x and -3 for y, we have +1/3. So notice we actually have a reflection here of values reversing positive and negative. So if -2, +2, -1, +1, -2/3, +2/3. Similarly, we have -1, +1, -3, +3, so we'll have +3/2 here. 1 and -1, +1/2 makes -1/2. +1/3 comes to -1/3. 2 and -2, 1 and -1, 2/3 and -2/3. And then our value here would have to be 3/2. So I'm going to start by putting my vertical slopes, then putting my 0 slopes, and I'm going to put my diagonal slopes all the way across here. I have a slope of 1. And on the next, I have a slope of -1. So notice we are going to have slant asymptotes in this equation. And then we would have slopes of 1/2 and 1/3, 2/3, then across here we have a slope of 1, then a slope of 2, and then a slope of 3. We have -1, -2, -3. And -3/2. Okay, on the mirror side, we have -3, -2, negative 3 halves, negative 1 half, negative 1 third, we have negative 2 thirds, 3, 2, 3 halves, positive 1 half, positive 1 third, positive 2 thirds, negative 1 third, negative 2 thirds, negative half. So notice that the shape we have is a hyperbola. We could either have a left opening hyperbola, left and right, or an up and down vertically opening hyperbola. It would really depend upon the point where we started. So in this case, we're going to do 3 possibilities. If we started at 0, 1, then our hyperbola would open this way. Okay, now what I want to point out on this is we're not allowed to go down and draw the bottom of the hyperbola. Whenever we find a dy dx and solve, we're actually getting a function, and functions have to pass the vertical line test. So you should not draw a piece that does not pass the vertical line test. That means if I start at the point 1, 0 here, that I would have to have more information to know which side I should draw. So I should either have this side or this side, but technically not both pieces. I should not actually have both pieces of this to pass the vertical line test. So we would actually need more information for that. Okay, for 0, 3, and I would really only have the top portion of the hyperbola. For the next piece, or the next problem, we have dy dx is x minus y. I again like to start with my zeros. So x minus y equals 0 if x equals y. So along the line y equals x. So 0, 0, 1 minus 1, 2 minus 2, 3 minus 3, negative 1 minus negative 1, etc. We're going to have 0 slope. Okay, substituting other values in, if x equals 0, along the x equals 0 part, that's 0 minus y, we'll have negative y. So this will be 3, 2, 1, negative 1, negative 2, negative 3. Similarly, if y equals 0, then we have x minus 0, so it's just the x value. So negative 3, negative 2, negative 1, 1, 2, and 3. So here, we would have negative 3 minus 3. X is negative 2 minus 3. Negative 1 minus 3. So notice the pattern, negative 6, negative 5, negative 4, negative 3. We can fill in the pattern. So notice, if we were to go here, negative 3, negative 2, negative 5, and then negative 4. So notice when you have a pattern, you can use that to help you fill in. So I'm filling in the pattern that each number, negative 6, negative 5, negative 4, negative 3, negative 2, negative 1, counts down 5, 4, 3, 2, negative 1, positive 1, and then positive 1, positive 2, 1, 2, 3, 1, 2, 3, 4, 3, 4, 5, and 4, 5, 6. So what's nice about this pattern is that along each diagonal, we're going to have the same slope. Kind of helps match those up. So along this diagonal, I'll have 0 slopes. And then below that, I'm going to have a slope of 1 the whole time. Makes it nice because I can draw the same slope. And then a slope of 2. So once I've chosen what I think the slope of 2 would look like, makes it a little nicer. And then a slope of 3. And 4s, 5s, and 6s almost start to become vertical, so you just want to make sure they get steeper as we increase the diagonals. So the next slope is -1. Oops, wrong spot. So -1. And then -2. -3. -4, 5, and 6 again get steeper as we go across. So we have 0 slopes along y equals x, and we do have a slant asymptote again. So now if we use the point 0, 0, we need to have that slope initially and then slowly alter our slope so that as we approach the asymptote, we have the same slope. And as we come between, in this diagonal, we need to have a slope of -1, but again, that doesn't mean that we make sharp turns to get there. We need to slowly and smoothly move through the slope field. So if I were to pass through the point 0, -1, that would be right on the slant asymptote. And then 1, -2 has to follow so that every time I go near a slope, I have a matching slope. So not necessarily on top, but just follow, slowly going between them so that your slopes match the slopes that you're close to. Now this one's kind of fun because what you're going to see is going to happen is then when your dy dx is sine x, what would be the antiderivative of sine? So if the slope is sine, the antiderivative of sine is negative cosine plus c. So our slope field should give us a pattern that show us a graph of negative cosine plus c. So on here, the x value is the only one that matters. The y value does not have any impact. We're only going to substitute the x in. So sine of negative pi is 0. Sine of -3 pi over 2 is in the same position as pi over 2, actually is 1. Negative pi over 2 is a -1. Sine of 0 is 0. Pi over 2 is 1. Pi is 0. And 3 pi over 2 is -1. So in filling out my slope fields at 0, we should always have 0. Pi over 2, we should have 1. At negative pi over 2, we have a slope of -1. At pi, we have a slope of 0. At negative pi, we also have a slope of 0. At -3 pi over 2, we have a slopes are 1. And at 3 pi over 2, our slopes were -1. Okay, so now if we start at 0, 0 and follow our slope field so that we can't go over again and just turn fast because we shouldn't have this kind of a sharp turn in here. We need to slowly move so that by the time we get to pi over 2, we have a slope of 1. And then slowly turn so that we have a slope of 0. And slowly turn until we have a slope of -1. And continue on in that manner. So what happens as we go across, if we continue, so that we have a negative slope, and a 0 slope, and a positive slope, continuing in this manner, you'll notice that we do in fact have a negative or an upside down reflected cosine graph. If we have started at pi over 2, 0, we would have actually had exactly the negative cosine graph. So this looks like negative cosine of x plus 1 and just negative cosine of x. Okay, for number 4, I again like to consider where I would have 0 slope. So I would have 0 slope if x equals 0. So everywhere here. I would have 0 slope if y equals negative 1. I'm going to have 0 slope if y equals 2. So that makes this a little easier to draw in. So that's the kind of thing that you'll be looking for on the AP exam, is where you would put your 0 slopes first. That's your first point out of 2. Okay, so then we're going to substitute in, if x is negative 3 and y is 3, we'll have negative 3 times 4, which is negative 12, times 5, which is actually positive. So negative 12 times 5 would be negative 60. So if we substitute negative 2 in, we get negative 2 times 4, which is negative 8. Negative 8 times 4 is negative 32. If we substitute negative 1 in for x, we get negative 1 times 4. Actually, let me start over. I think I'm miscalculating my values. There we go. So we substitute in, we get y is 3, so this is 4, and negative 1, so negative 4 times negative 3 is positive 12, sorry. If we substitute negative 2 times 4, negative 8, times negative 1, positive 8, negative 1 times 4, negative 4, times negative 1, positive 4. If x is 1 and y is 3, we have 1 times 4 times negative 1, so negative 4. 2 times 4 times negative 1 is negative 8. And then we get negative 12. If y is 1 and x is negative 3, we'll have negative 3 times 2, negative 6 times 1. And so we get negative 6. Negative 2 times 2 is negative 4 times 1. Then negative 1 times 2 times 1 is negative 2. And 1 times 2 times 1 is 2. So notice that we get the pattern again of reflecting across. So if the y value is 0, we're going to get 2 times 1 times the x value. So 2 times x. Negative 6, negative 4, negative 2, 2, 4, and 6 again. And so if we substitute in negative 2 for the y value, we're going to get 4 times negative 1. So negative 4 times the x. So negative 4 times negative 3, negative 4 times negative 2, negative 4 times negative 1. So see how we're repeating a pattern from the top? If we have negative 3 for the y value, we'll have 5 times negative 2. So we'll have negative 10 times the x, which is 30, 20, 10, negative 10, negative 20, negative 30. So for putting our values in, if I want to work between the two zeros, we really have a slope of positive 2, positive 4, positive 6. On the left side we have negative 2, negative 4, negative 6. And if we look above and below, we have a slope of 12, 8, 4. So on the other side we have 12, 8, 4, and negative 4, negative 8, negative 12. Below we have a slope of 12, 8, 4. Negative 4. My computer's a little glitchy, sorry. Negative 8, negative 12. And then below we have a slope of 30, 20, 10, negative 10, negative 20, negative 30. So if you want a better idea of what's happening at your horizontal asymptotes, the way that this is curving around, you could do a value in between, such as one at y equals negative a half. So if we had y equals negative a half, we would have x times 1/2 times 5/2, or x times 5/4. So it could be interesting if we used positive 2, which would make 2.5. And see that our values would be coming around, getting closer to the asymptote to flatten out. So if we were going through 0, 0, we'd have to have a 0 slope. It goes steeper, and eventually this would have to flatten out. If we're passing through 0, 1, we'd have to flatten out a little faster, so it just wouldn't have as steep a curve ever. So it would depend on where we were. So if we had a point such as 0, negative 2, we would just never approach that asymptote. So you'd have a drastically different curve depending upon where you started your point. Okay, so given the following differential equations, sketch the slope field for each. So if the derivative equals 2, that means the derivative is always 2. So no matter where we are, the slope is always 2. So what has a derivative that's always 2? Well, that would mean that y would have to be 2x plus c. So the plus c means that any of these could be our solution. Actually, there are infinitely many because we could have all the values halfway between as well, or a quarter of the way. So it doesn't really know what value we have. We simply know that we have any line that has a slope of 2 would be our possible solution. So that's actually called a family of solutions. So if our line passed through the point 1, 3, then our C value would have to be 1. If we pass through the point -2, -2, our C value would have to be 2. Okay, so for this next one, our slopes are negative x. So if x is -1, the slope has to be 1. If x is -2, the slope has to be 2. If x is -3, the slope has to be +3. X is -4, the slope is +4. And then +5, etc. On the other side, the slope, if x is 1, would be -1. If x is 2, the slope would have to be -2. And then -3, -4, and then -5. Just as a hint, the way that I actually figure out how I'm going to draw mine, if I have a slope of 1, I'm actually considering just the box here. A slope of 2 would be like there, 3, 4, etc. So I have an idea of what the slope should look like. And again, as long as you're getting the steepness right, that they get steeper. So get the zeros and the ones and negative ones and the verticals correctly, and then try to make the others just match the steepness. So notice if I were to anti-derive this, I would get -1/2 x squared plus c. So these do look like negative parabolas. If x is 0, I do have a 0 slope, because -0 is still 0. So if we're passing through the point 1, 3, we would need to have a parabola that matched this one, or something close to that. So notice what I've done here is really kind of bad. I really don't match the slopes that I'm around. So I really kind of want to fix that a little bit, so that as I go down and across. So just kind of try to do a little bit at a time rather than one solid stroke, so that you're matching whichever lines you're really close to at that particular time. Okay, so then if I were to do -2, 2, it's going to be a very similar curve. A little higher. Have a very similar pattern to it. Okay, for the next one, I'm going to start with putting, if x equals 0, the slope is 0. If y equals 0, the slope is undefined. It does not exist. So for x equals 0, slope is 0. If y equals 0, the slope is undefined. Remember I said that that would always win. So in choosing, I have to choose the vertical at the origin. And now if I were to try to make points here, if x were 1, let's let x equal 1 the whole time, then we'd have -2 over y. So -2 over 1 would be -2, -2 over 2 would be -1, Negative 2 over 3 is negative 2/3. Negative 1/2. Negative 2/5. If x is 1, we have negative 2 over negative 1, be positive 2. Sorry, yeah, okay. And then positive 1, positive 2/3, positive 1/2, positive 2/5. Okay, if x were 2, we're going to have negative 4 over y. So negative 4 over 1, positive 4 over 1. Negative 4 over 2, positive 4 over 2. Negative 4 over 3, positive 4 over 3. Negative 4 over 4, positive 4 over 4. Negative 4 over 5, positive 4 over 5. So notice what's happening. We can mirror image. If x were negative, it would simply change the sign. So we can actually mirror the ones from previously across that get flatter as we go up. Like so. So notice what we're getting here. Now this one is very similar to the circle one we saw earlier. So I'm going to quickly fill these in. You can calculate the exact values as we're going through. The difference between this and the circle is because of the imbalance between the x and the y. We don't get an actual circle, we get an oval. So if we're going through the point 0, 0, there's really nowhere to go because the center of the circle is 0. There's not really a graph there. If we're going through the point 0, 3, however, we would have an elliptical shape. So in here. So notice if we have dy dx is negative x over y, we always had a circle at the origin. But if we have dy dx is equal to negative ax over by, where a and b are different, we end up with an ellipse that is centered also at the origin. Okay, so we're going to do matching again. And we're going to start first with sketching through. So if we have -1, -1, which would be here, we would have a line with a slope of 1. So, sorry about that. A -1, +1 be here. Okay, 1, 2. Different line with a slope of 1. And 1/2, -3/2. Again, another slope of 1, but still just a line. Okay, so if we have the point, if dy dx is negative x, notice we have an upside down parabola. So at -2, 1, we would want to follow the slope fields. So again, not necessarily in one long stroke. Just try to make sure that you're never competing with the slopes that are shown. Your slopes should always be very similar to the slopes that they're very nearby. We use 2, negative a half. And then finally, if we were to do 1, negative 2. So as for the next one, the derivative is sine of x, going through 0, 2. We have an upside down cosine graph. We do 1, negative 1. We still have an upside down cosine graph, but shifted to a different height. And through negative 2, negative 2. That's still different. Upside down cosine graph. Plus or minus c is the difference. Okay. So here I'm going to start with finding my zeros. So if x equals negative 1, I'm going to have 0 slope. If x equals 0, I'll have a slope of 1. If x equals 1, I'll have a slope of 2, and then 3, and then 4. So I'm doing this quickly because I know where 1 is, and 2, and I'm just doing steepness. Got my 0, I have my 1, and they simply get steeper as we go across. So if x is negative 1, we have a slope of 0. If x is negative 2, we have a slope of negative 1. So I'm going to get that one pretty spot on. And after that, they really just get steeper. If I let y equals 0, I have a 0 slope. If y equals 1, I have a slope of 2. And then it would be 4. So notice they simply got steeper. At negative 1, I would have a slope of negative 2. And then negative 4. And I'm going to use my zeros. So if y equals 1, I'll have a 0 slope. If y equals 2, I would have a slope of 1. If y equals 0, I would have a slope of negative 1. And then negative 2. And then negative 3. So again, just doing steepness other than the zeros and ones, making sure I have the right positive or negative each time. So if x equals 0, I have a slope of 0. If x equals 1, I'm going to have a slope of 2. And then 4. And then 6. Negative 2. Negative 4. And negative 6. Okay, so now we are on to our matching page, and it's our last page. Now, this is a little different. I did put the instructions at the bottom. If you have an 89, just a couple of you do, you can actually graph slope fields on your calculator for each of the derivatives. But these are the y functions, so not the derivatives themselves. So this is saying that the equation is y equals 1 plus or minus c. So if y equals 1, that would be a horizontal line, and then plus or minus c, could be up or down, would be d. If y equals x squared plus or minus c, then that would be letter C. If y equals 1 over x squared plus or minus c, then 1 over x squared would be a. So it helps to know what your parent functions look like. And again, you use dy dx to draw the lines, but the graphs look like y, because that is exactly what you're getting, the y value. You're using dy dx to approximately draw the graph of y plus or minus c. So if y equals cosine of x plus or minus c, then your graph should look like cosine of x plus or minus c. So the answer would be B. If y equals x plus or minus c, then the answer would be H. If y equals x exactly, or shift it up or down. 1/6x cubed needs to look like a cubic graph. So that was F. If y equals sine of x, then the graph should be sine of x exactly, plus or minus c. So then the natural log of the absolute value of x actually has two sides. But then we have plus or minus c. So that's this graph. We actually have verticals, but you can rarely ever see the zeros or verticals if they're actually on the axes. So G. So you use dy dx to draw the lines to make a graph that looks like y. So when you're doing the matching, the y is what it looks like. When we're doing matching with dy, the dy's give us the derivative, which gives us slopes to plot. So when I'm doing the derivative, I can look for the derivative equal to 0 to help me. The derivative equal to 0 being positive or negative to help me figure out which graph based off the slopes. But again, the graphs should always look like the y values.